Thank you for joining this session on generative models. We're here to tell you about a very exciting project on the use of AI for privacy. I'm Jessie Lamontagne, and I'm a data scientist at a major financial institution in Canada. Today, I'll talk to you about a research partnership I led with the University of Alberta on the use of generative models to create synthetic transaction datasets. Transaction is a domain that's very understudied because people feel quite strongly, and rightfully so, that the way they transact is a private matter. I'm interested in transaction because I believe that the way people behave in the transaction space holds a lot of information that they could harness to achieve their goals. At the same time, I take a very customer-centric view of data science. For a data scientist like me, the most customer-centric thing to do is to safeguard the data. So this project was designed to add a layer of privacy to our customer data. I started thinking about this idea when I first joined the bank, and I observed that in order to collaborate on an efficient project, we had to go through a very onerous process that really slowed down the pace of engagement. I thought there had to be another way. But if we could make synthetic data so good, it could be used to train a machine learning model. If you're thinking, wait, synthetic data is not hard to make, I can just generate some values from a distribution. That kind of synthetic data doesn't allow you to build a model that will transfer well to real-life data. Maybe you're thinking, isn't there a library in Python called Synthetic Data Vault? Well, that will give you the tools to synthesize tabular, time series, or relational data. Transactions are a very special type of data called a panel. Panel data holds a lot of information because you can observe the same individuals over time. The challenge in synthesizing a panel is that you have to capture both the time dimension and the individual, the person's dimension. In the process of learning about the patterns over multiple dimensions, we can learn a lot about the behavior of people when it comes to transaction, and that can help us serve them better. Generative models are one of the most powerful tools at our disposal today for unsupervised learning. It so happens that banks have a lot of unlabeled data. Here's how generative models work. You start with some distribution, say a unit Gaussian like I have here, and the model will try to generate an output. And it will ask, does this look like the input? Not really. So it imposes a loss and try again. It tries again and again until it learns the patterns in the data. But what does a transaction look like? So here we have a really fun data science challenge in the sense that we could think of a few neural net architectures that might allow us to capture the time and the customer dimension. But we also knew it would be difficult to tell if the model had really learned the patterns in the data. The data set we used for this model is based on the raw data that comes from the authorization system for card transaction. It contains information about the transaction itself, the type of card used, and the merchant. The subset of this data set that was used to train the model represents more than 1 terabyte of data. Needless to say, we couldn't have done it without GPU. A transaction is characterized in the data as a high-dimensional but very sparse matrix. It's a mix of continuous and discrete variable, and as I mentioned before, we know there are both individual patterns, like this fictitious customer here is someone who uses their cards on a regular basis, but prefers to pay by a credit card for a restaurant meal. And we know that there are time patterns in the data. For example, people spend a lot more money in December than they do in January. So given that we had a lot of potential features in the data set, but a lot of them had quite sparse representation, we had to distill to what we think is the essence of a transaction. And those are the features we used in our model. The graph here is called a Pareto frontier. It represents the surface of the potential choice space given available technology. It's an abstract way to think about the fact that when synthesizing data, we have two competing objectives. On the one hand, we want a very private data set. And an example of a very private data set would be pure white noise. At one point in this project, we forgot to connect 2 layers and ended up with that. On the other hand, we want a useful data set. And the most useful data set we could get is the original data set, as is. So we start from some point in the middle. And we want to expand the Pareto frontier so that for a given privacy level, we have more utility, or for a given utility level, more privacy. But this takes us back to the fact that it's hard to tell if a data set is really private, or to know if it will be useful. How can we tell if we have a good set of synthetic customers? When it comes to privacy, we can build it into the design of the model itself by turning to probabilistic models. André will expand on this, but the model is designed to first learn about the patterns in the data and to compress those patterns into a lower dimensional space or latent space before taking a random sample from that latent space to reconstruct the data. That random sampling is what takes us away from the initial data and creates new data that represents nobody from the original dataset. Of course, we're not going to assume that this is true. We can calculate the odds that a real and a synthetic customer have the same two transactions in a row, for example, and then we can check if it happens by chance in the data. We can check if two customers from the real dataset are closer together than they are to an individual from the synthetic dataset. And we can inspect individuals with similar patterns across the two datasets and make sure that none of them are actually the same. To tell if a synthetic data is going to be useful, we're going to start by doing some distributional analysis. We want the pattern in the data to hold at a distributional level. So for example, the average transaction amount should be similar, but so should the higher moment of the amount distribution, so that if we plot the two distributions for the synthetic dataset and for the original dataset, they overlap. We can do this one dimension at a time. And we can also look at measures of distributional overlap. Here, I want to pause to ask you to think about the way you might measure the overlap between a high-dimensional distribution where some features are continuous and some others are discrete. I'd love to hear about it in the chat and to talk with you about this. Finally, we'd want to use the dataset in a machine learning model and see if the model generalizes to the real data. That's the real test. I'll pass it to André now, who'll tell you more about the kind of models we built.
We chose Variational encoder as the AI model for the task. The Variational encoder consists of two parts, an encoder and a decoder. An encoder compresses the data into the latent space of the desirable size, and a decoder brings it back to its original form. And the loss function tries to minimize the difference between the input and output. Now, the goal of the variational encoder is to learn a probability distribution over a multidimensional variable. But what's so nice about it is that it allows each dimension in the representation to push themselves as farther as possible from the other factors, giving in this way a nice spectrum of the factors and making sampling a very interesting task. How are we going to input those transactions into the variational encoder? Transactions to tell a story as images. A convolutional neural network essentially has a window, and this window goes through the image on a given stride, convoluting those values into a single value or in a smaller window size. And that makes it compress the data into a smaller image, and you can keep doing this until a desirable size. Now, how to put the transactions into images so they can be convoluted can be done in more than one way. Because first of all, an image has three dimensions. It has the width, has the length, but also has the channels. So first of all, features were represented in the channels of the image. The reason is that it doesn't matter the order of the channels for the convolution that we're doing. Because if you actually put the features as columns or rows, the convolution would have a different meaning. Hence, we have features as channels. The second key point is we use the time of the transaction as the pixel position in the image. So for instance, a transaction that will happen on January 1st will be the very first pixel on the image, and the transaction that will happen on December 31st will go as the last position, the last pixel of the image. So far so good. Hence we have now a transaction to image. However, it gave us a lot of very sparse images. That means a lot of images with blank spots. And then convolution on those images are not as efficient. Instead of having a time as a position, we stacked all transactions one after the other in a string of transactions in an image. And we add one extra feature, and this feature being the interval between the transaction. So for a transaction that happened now, how long did it take from the transaction before that? So we gave one more feature to be learned by the model. And how to deal with so many data? Obviously, we need some help from parallel computing with GPUs. And we used 8 GPUs for those tasks. And we used the latest technology on those GPUs with Rapids. So we used QGF, QPy, we used Dask and Dask QGF as well. Without them, we could not even start. You cannot even compare to the task without them because this massive quantity of data that we had. And what was the whole process to the point of start training? We had, of course, the data cleaning of dealing with outliers. We had the process of transforming the data into the range appropriate for the VAE. And we have the stacking of the transactions into images and the converting the features into channels, which is not so simple. And even with all those tools, with Dask QGF, sometimes we have to go to a second solution or a third solution for one that will handle all this massive input data to then transform to the desired output. One thing that was important that helped was to give a hand to our model so we could easily find those clusters at the beginning on the latent space. We did that by finding some rough clusters on the data itself before the preprocessing, just to add labels to those data. Those labels didn't mean anything. It just meant the proximity that you have between of users. Some users will roughly kind of cluster together. Those clusters were obtained going to TSNE and K-means clustering, and just helped at the beginning by having some importance that progressively decreased over the epochs to just form those initial clustering. We had many variations on VAE by itself, but also how we deal with that, how we do convolution, the clusterings, how many layers. So there was an extensive hyperparameter search to get to the best option of all those variations of the model we have. And here, for instance, we see in one of them the clustering that we had. Here, our latent space was reduced to just 10, so 10 clusters. There's so many things that we can improve. Right now, we do have a good, useful data set that is truly private, but we want to match as much as we can on the utility set as we have on the privacy set. And we have to have control and, of course, have a peace of mind that our model is truly secure and good for usage for all those goals Jessie gave us at the beginning, using the metrics that also she gave us at the beginning. And we're still very excited to keep working this project because, yes, we answered some questions, but so many more appeared. So there's so many things to do, so many possibilities. The data by itself are so new and so many things to unveil. The technology, how we approach that, is one of many that can be done, and even it has so many variations because the data is so new, and the tricks we have to find to match them was so interesting. But most importantly, is the fact that we saw a new fresh look on AI, where yes, we're producing fake data, but for privacy and for security. We're not trying to trick, we're using AI for good. And I think that can inspire some of you to also use AI for good, to find the good things AI can bring, not only the bad, because we know about those things. But there's so much power, so much things to discover that AI still can enable us to do. Thank you for attending our talk today. We really appreciate your time and we hope you enjoyed as much as we did. If you have any further questions, you can also use Jess's email as you can see in this slide. Thank you. Have a good one.